cross-site request forgery is really one of those foundational vulnerabilities that I think every hacker should be aware of. It's seldom seen by itself nowadays, as defenses are often baked into frameworks, but we can often access it with bug chains like cross-site scripting. That being said, it's a very high impact bug, so if we can actually trigger it, then we can definitely expect a big payout for it. And in this video, I'll walk through what cross-site request forgery is, what some of the most common defenses for it are, and how we can look to bypass it by chaining other bugs or by looking at misconfigurations that the developers have put in place. Before we continue though, I'd like to recommend you to watch my previous episode on CORS misconfigurations, as it really goes into the foundations of client-side attacks that will be very important for this episode as well. Well, for those of you who haven't watched the video, then a client-side attack is basically when we induce a victim to click on a link which either redirects them to our website or redirects them to the target website, and we can get some kind of cross-site scripting there. So it is important to realize that client-side attacks are possible because the browser stores credentials in cookies, which we can then use to make requests on the user's behalf. So when the user clicks on our website, we can fire off some JavaScript using some programming. We can use, for example, the fetch API, and then the victim's cookies are automatically included when we send it to that website. So the website can't actually distinguish whether or not we, as the website, as the attacker's website, are sending the requests on behalf of the user, or if the user is actually on the website sending the request themselves. So to the website, that's basically the same. And obviously it's a bit of an issue if you can perform actions on behalf of a user on a website. So that's where cross-site request forgery basically comes from. It's where a user goes onto your website and you can perform actions on behalf of the user when they're in your website by utilizing their browser cookies. So, little diagram there. So what is important to realize is that we can't actually see the response from these requests. At least normally not, we can't, because it's blocked by the cross-origin resource sharing policy that I talked about in the previous episode. But for actions like post requests, put requests, or delete requests, we don't actually need to see the response. And that is because when the action gets performed, then it's already been done, and we can send requests wherever we want to. But CORS only blocks sending requests and then receiving the response. It doesn't actually block the request itself. So that's what makes cross-site request forgery possible. And that's why websites actually need to mitigate against cross-site request forgery as well. So here I've set up a little demo to show you what cross-site request forgery actually looks like in the cold hard code. So here I'm playing the role of the victim here. I'm going to click on the attacker's website, and on the left you can see the code for the attacker's website, which is what we're looking at on the right. It's kind of just a blank screen, but it's a script here with a fetch request with JavaScript. So what this is going to do here is that it's going to send a request to the URL here, and it's going to send the data, which is right here. It's going to send this username, and it's hopefully going to change it to pond, which is going to perform an action on behalf of the user. This is the main website. This is kind of like the target website, and it's hosted on my domain here. So what we're going to do is, as the victim, we're going to go in and we're going to log in. So we've been logged in now. Now hopefully, yeah, you can see that we've been logged in as a victim user. So we can change our own username here. Obviously we can say like, we can change it to like Jacob or something. So there you go, it's been updated, which is nice. Everything's working as expected. We can refresh the page. Actually, maybe we don't really want to do that. Yeah, we can refresh the page here and you can see it still says Jacob. So I haven't coded in any CSRF defense here. So let's have a look at the request here. So let me just get rid of that screen. There you go. So you can see here we have our cookies there, and we'll just change this, for example, to Jacob1 just to show you that request here. And there's currently no CSRF defense here at all. So it's just sending in a username. That's for a later example. Well, there's our session ID, there's our cookie. So the attacker has access to sending that. And yeah, so if we change this to, for example, Jacob2, you can see that it's been changed. So if you see something like this, you see a request that doesn't have any CSRF tokens in it whatsoever, and like for example, if you see something like this and you like remove it or something like that, and it still works, then probably means that it's vulnerable to CSRF, right? So what we can do is we can create a POC. We can basically create a website like this and then induce the victim to click on it, right? So now we're going to simulate that, right? So here we have our API, and it's basically, you see what this is doing is it's just going to send the form in. It's just going to send this as username, but instead of Jacob is going to be Pond. So, and it's going to use my credentials. Its credentials include means that it's basically using my credentials to send it, right? So we're going to refresh the page here. So we visited the attacker's website. We have clicked on the dodgy link. Now let's go back and see what happened. I'm not going to do that, sorry. I'm going to do this. And you can see now my username has been changed. Well, so that's basically what client-side vulnerabilities look like. That's what CSRF is. It's when you can perform actions like changing the username on behalf of the user. And it happens because, as you can see here, I haven't coded any CSRF protection. Right, so that's a vulnerable website that has no CSRF protections. In that case, how do websites protect against CSRF? So one of the ways I'm going to show you is this double signature cookie. I think it's called double. I think I just called it double. 1 second. Okay, here we still have our old username here, and that just changes back to Jacob, so it's gonna make sense, right? So here we have our user again. So this website isn't vulnerable to CSRF, and we're going to see why. So I'm going to try and, for example, change this like test or something like that, right? And you can immediately see in the request body, you can see a new parameter has appeared. And this is the CSRF parameter we showed before, right? So it's the same one as it's there, right? So if I send this in, see that it's updated correctly, right? So how is this protected? So we have the CSRF token in our cookies, and then we have one of these in our request body. And what the server is basically doing is it's going to check if this token here is the same as this token here. And it's as simple as that. There's no other defense basically. And the reason this works is because as an attacker, we can't actually modify or see the user's cookies. We can only send them on their behalf. But the browser won't let us look at them. If it's a third-party website, that is. So, by doing it like this, the website can set a random cookie, like a 20-digit base 64 value, and then when it's being rendered on the server side, it can return this cookie to the user, and it will be included in the form data like so. So it doesn't actually matter what these numbers are, right? So if I change this like deer and like something like this, like just one letter character, you can see that still works. But if they don't match up, the server will not allow the request to be sent. You can see I've changed this and now it says invalid CSRF token. Maybe I'll change it to something else so you can actually see it working. Yeah, you can see invalid CSRF token and the username hasn't changed. And you can see the CSRF token included in the actual form here, right? So if you see here, you can see this input hidden and it says CSRF value. So when the server generates the HTML on the server side, it just includes this value from the cookie in the request, right? So when I try and get it, then that's where the value goes. Yeah, so if these cookies don't match up, then the request will be rejected, and the server generates that on the server side and then includes it in the value here, hopefully sanitizing the HTML as well, knowing that this is a PHP website, probably not sanitized. So that's one of the ways that websites defend against cross-site request forgery. And the second way, which I'll show you, there's loads of ways, but these are kind of the main two I've seen anyway, which is when cross-site request forgery, the CSRF token, is tied to the user's session. So we're going to go to session.php, and this is the sort of same session that we're using, but I'll show you this one as well. So and we'll change this to test3 as well. So send that in there, and you can see that this CSRF token, it's not related to the cookie at all, and we don't really know where it comes from, right? So it's not actually related to anything in our request. So even if I get rid of this cookie here and I change, I get rid of this cookie here, and for example I send it like that, it'll still work. And if I, for example, change this to 0, it won't work. So the way that this server defends against CSRF is that for every session ID, which you can see here, it assigns a separate CSRF token. So it has it stored somewhere in like the cache or the database. And if we don't provide the correct one, then it won't accept the request. And it basically works the same as in the server side, in the double cookie method, where it just appends the value on server side rendering. It fetches our CSRF token from the database and it'll just append it there. So with the double cookie method, there is a kind of way to bypass it. That is, if as the attacker we find a way to set cookies for the user on the website, for example through like a subdomain, if we're able to set cookies for the user, what we can actually do is a technique called, I think it's called cookie tossing or cookie bombing, where we can actually flood the browser with cookies, and then after a while it will kind of like start reducing some of getting rid of some of them. Or we can also try and send our own CSRF token in to basically replace the one that the user has. So if we go back here, right, if I'm able to set the user's cookies, I could set the CSRF token to whatever I want to, and then it doesn't actually matter what this value is. We can set this like 1, and then we can perform any action on behalf of the user because their CSRF token will be 1. So that's one of the ways that we can basically bypass the CSRF token there, or we can try and find a way to get rid of this cookie entirely. But in this method, where the server stores the CSRF token in the database, it's actually more secure because it is not tied to anything in the actual request. It's just tied to what the server is looking at in the database. So even if we were able to completely control this request, we wouldn't be able to perform actions on behalf of the victim because we just don't know what this CSRF token is. And so in order to bypass this method, what we basically have to do is try and leak this token. And you can see it's right here, right? So if we're able to see the response in this request, we can see the CSRF token, right? So if, for example, CORS is misconfigured, we could look at this and try and steal the CSRF token that way. Well, that's pretty much the only way that you're able to bypass this type of CSRF protection. That's, of course, the CSRF token here doesn't actually do anything. Sometimes that happens, where, for example, the framework has the CSRF token attached, but the server doesn't actually validate it. So you can test for that as well. But this one is definitely more secure than the other cookie method. And then this one last method, which isn't actually like a defense at all. It's not something that the server implements, but it's basically utilizing CORS to defend against CSRF. And basically, I'll show you this request as well. You can see that it looks a little bit different, right? So there you go. So you can see the format that we're sending the request in, the content type is different. It's in JSON. And why is that important? So basically, the way cross-origin resource sharing works is it doesn't actually allow us to send JSON data to third-party websites unless it's specifically allowed by that website. So the browser will never allow us to send this type of data, this JSON data, to another website that isn't in a different origin unless it's specifically allowed by that origin, even in a post request, pull request, or whatever. And that's basically one way that we can defend against CSRF is by just requiring the data to be sent in JSON, because that means that no third party is able to send that data to us. By default, only I think only three data types are allowed, just text/plain, or it's at the form, right? So the form URL encoded, this thing right here, right? There's one more, I forgot it though. But those three main types are allowed, and JSON isn't one of them. And neither is something like XML, which is also used sometimes for APIs. So this basically serves as a kind of CSRF protection, even though it's not something that's actually implemented by the server. It's just kind of an innate protection offered by the cross-storage and resource sharing policy. So how could we bypass this, right? So say the server accepts something like this. So it accepts text/plain content type, but it it kind of reads it as JSON, right? So even though we sent this content type as text/plain, if the server still reads it, which it might in this case actually, is it? Oh, PHP websites, man, they're vulnerable to everything, aren't they? Nah, if the content type text/plain is accepted by the server, then we are able to send it like this, right? Because basically we can just send these two brackets in the username on behalf of the victim, and then the server will interpret this as JSON. This is, I think, against the RFC standards. The server shouldn't accept text/plain and then read it as JSON. The server should say, no, you're not allowed to do this. But some servers do allow this as well, and this is especially powerful if it's like an API or like GraphQL or something like that. Because if it's accepted, then you can pretty much do anything on behalf of the user. That's why it's still recommended to put CSRF protection in JSON, even though it's kind of protected on by itself, right? So good, reliable, and secure websites will still do that. If the website's kind of like skipping steps here, it's not putting in CSRF protection, you could try and exploit it that way, and you could look for chaining other vulnerabilities to exploit it, like trying to get some kind of like markdown injection and get like a link to like send this content type properly as JSON. It's still not very secure, but I have seen basically CSRF protection get completely thrown out the window when it's JSON data. So that's the three main ways I've seen for defending CSRF, and now we're going to look at some real bug bounty examples from the real world. So this is a report sent to HackerOne, which is a bug bounty platform. Basically, you can send reports about other bug bounty programs to it, and they have their own program for securing HackerOne. And in this case, I think this is a very interesting report, as it's kind of like a theoretical report, right? So the bug hunter previously submitted a report where he was able to inject arbitrary HTML into the website, and now he found a way to escalate that into a cross-site request forgery attack, even though his previous vulnerability got patched before that, so he couldn't actually execute it. So he had to like theoretically show a way that he could have performed cross-site request forgery if the vulnerability was still there, and he got paid for it, which is interesting. So basically, the vulnerability was that he was able to leak the cross-site request forgery token, the CSRF token that we used before to prevent the actions from being performed on the victim's behalf, right? And I think HackerOne uses the session method, where each session has a separate CSRF token. So in this case, the token is just included on the website, right? And what basically happened was, if you clicked on a link in Markdown like this, in this one, and you made it as a post request, then HackerOne automatically appended the CSRF token. So you could inject HTML like this, and using a special attribute, which I think HackerOne handles as a post request, you could basically convince the server to send the CSRF token, right? So in this case, this was an attacker controlled website, and he was trying to get the victim to click on this, right? So he had to use the console to show this vulnerability because this obviously was patched before that. But what would happen is the victim would click on like a little button on the web page, which was put there by the attacker. And when they click the button, their CSRF token was sent to the attacker's website, and the attacker could then trick the victim to visit their website as well, and then perform any action on their behalf because they had their CSRF token now. So in this case, they could like invite themselves into their like book bounty program or something like that. So the attack scenario would be like you send a victim some kind of like button with HTML in it. Victim clicks on it. It redirects them to the attacker's website. Simultaneously, the attacker's website reads their CSRF token, creates this form here, and then auto submits it for the victim in order to basically perform any actions on their behalf. So, very interesting vulnerability. Yeah, except that the attacker already submitted a previous HTML injection, so they had to make this theoretical attack, and it was fixed, and they were rewarded for this. So, and that is interesting to note that you can submit reports like this in post, even though they're not possible, and a lot of programs don't accept theoretical vulnerabilities. But and while I'm talking about this report here as well, I want to talk about some of the developments in CSRF. And most notably, I want to talk about the same site cookie attribute. And what the same site cookie attribute does is when I mentioned that the browser store the credentials, right? And that any third party website can use them, well, that's not entirely true now because the same site cookie actually limits what websites can and can't use your user credentials. And by default in Chrome, the same site cookie is set to lax, which means that only websites with the same origin are able to use these cookies for post requests. And if I show you here, right? So if I go to the login page and I just post it and I just send a GET request like this. So, oh, yeah, if I send a GET request like this, you can see the same site attribute right here. And I've deliberately set this to none so that my example works. But if I didn't set this, then it would be set to lax, which would actually prevent this from working completely because I then couldn't use the cookies on this website from my attacker website, right? Because it's a different origin. So I, on this website here that I've coded before, will not be able to use the attacker's cookies, actually for post requests. So that obviously makes it very difficult to exploit cross-site request forgery, because unless the website deliberately sets the cookies to be available to all websites, then I can't send post requests on behalf of the user. So is CSRF dead? Well, not exactly, right? So that lax cookie applies to post requests. It still allows GET requests. So GET requests shouldn't actually perform changes. It is against the RFC rules, or like the internet rules, for GET requests to make changes on behalf of the user. But some websites still do this. So there are a lot of reports, especially on HackerOne, of websites that accidentally included changes in GET requests, forgetting that it doesn't have that CSRF protection. And so if you're able to find something like that, then you could still basically execute a CSRF attack. And then another thing is if you're able to exploit CSRF from the same website. Now, that might sound a bit confusing, but it's kind of a new sort of phase in the bug bounty world. It's called client-side. I think it's called client-side request forgery, where instead of using it from a different website, you try and use the target website to actually send a request on behalf of the user. So how this could work, right, is imagine you had a website and there was a parameter in like the URL, which was like website, right, something like that. And that parameter controlled, for example, a post request that the website would send. Like you could control the path of a post request that the website was going to send. If that is true, then you can change that path to be whatever you want it to, and you could execute CSRF that way, right? And that's becoming increasingly common because many websites now use client-side rendering like React to basically load up their websites. And so they have to rely on a lot of JavaScript to do their rendering for them, including post and get requests to like microservice APIs. And if we can find a way to exploit that by using unsanitized parameters, we could potentially send post requests on behalf of the users from the same website using their cookies while basically bypassing the same site lags problem. We're basically doing cross-site request forgery from the same site, which is interesting definitely, but it's where the research I think is going nowadays. And we're seeing that increasingly more with stuff like client-side path traversals as well, which is a path traversal inside the user's browser. So going back directories, and that again can be used for CSRF purposes as well. So anyway, I hope you found this video helpful and that it gave you some insights into cross-site request forgery. And I also recommend you to watch my previous episode on Hacktivity Explained, where I go over an actual CSR vulnerability, which was changed with the CORS misconfiguration to leak the user's CSRF token, very similar to the vulnerability we saw here before. And I also go over an SSR vulnerability, and that is a local file read into an SSRF chain, which is also very interesting. And as always, hope you enjoyed the video and happy hunting.